Okay. First of all, tell me, what is a device used to measure current called? Which device is used to measure current?
Meter.
Okay. Is that the only instrument that can measure current?
Galvanometer can be converted into
Okay,
ammeter.
fine. So you can use an ammeter or a galvanometer to measure currents. What's the difference between an ammeter and a galvanometer? Okay. See, galvanometer measures very small currents. Okay. What do we mean by very small currents? Usually it will be in the range of milliampere. Okay. That's 1/1000th of an ampere. So 1 to 10 milliampere or something like that. It will be in that range. And mostly galvanometers are used to detect currents, just to know if any current is passing in a wire or not. Okay, we use a galvanometer. We just connect the galvanometer along that wire. And if there's a current passing, it will show deflection. Even for small currents, it will deflect. How exactly a galvanometer works, that we will learn in the next chapter, moving charges and magnetism. Okay, after we learn the concepts of moving charges and magnetism, its application is in a galvanometer, ammeter, and voltmeter. Okay, so that we'll see at the end. But just remember, this is a device used to detect currents. And ammeter measures much higher currents than what a galvanometer can measure. Okay, so both are used to measure current itself. Galvanometer for small currents, ammeter for larger currents. Okay, what is the device used to measure potential differences called? If you want to measure the potential difference between 2 points in a circuit, which device can we use?
Potentiometer, sir.
Okay, fine. So potential difference can be measured using a potentiometer. That's okay. Any other device? Okay, you can use a voltmeter also. In fact, voltmeter also can be made from a galvanometer. Again, you'll learn that in the next chapter, how to convert a galvanometer to ammeter and voltmeter. Potentiometer we'll learn in this chapter itself. So these two are devices used to measure potential differences, potentiometer and voltmeter. Okay. Now, suppose you want to measure the current in a circuit. Let's take a basic circuit like this. Some battery having an EMF V, and let's say there are two resistors R1 and R2. Now, if you want to measure how much current flows in this wire, calculation you can do theoretically, V divided by R1 plus R2, that's fine. So if you want to measure current, what you will do is you will connect the ammeter in series with that wire. Okay, so just connect the ammeter here. Ammeter or galvanometer also you can. For small currents, you use galvanometer. For large currents, ammeter. Connect it here and it will tell you how much current is flowing. For now, we will assume the ammeter is ideal. Okay, what do we mean by an ideal ammeter? Now see, your aim was to measure the current in that wire. But to measure that, what you did, you introduced another instrument in that wire, along that wire. Now that new instrument ammeter that you introduced could increase the resistance of the network. Fine, you will learn in the next chapter. Galvanometer has a coil inside it, so ammeter also will have a coil inside it. There's a long wire wound inside, and since there is a wire, there will be some resistance. So ammeter has some resistance. An ideal ammeter has zero resistance. Okay, so whatever current was flowing along this wire, in the absence of ammeter, the same current will flow even if the ammeter is connected. That is what we mean by an ideal ammeter. It does not offer any resistance. Okay, and it will simply tell you the current that would have passed in that wire when the ammeter was not there. Okay, had the ammeter not been there. So if you want to measure the current in any wire, you have to connect the ammeter in series with that wire. Okay, most of you will be knowing this. Next, voltmeter. Voltmeter, as I said, you can use it to measure the potential difference between 2 points. Suppose you want to know what is the potential difference across this resistance. Then you have to connect a voltmeter between these 2 points. And how do you connect it? You have to connect it in parallel. In parallel to what? In parallel to whatever already exists between those 2 points. You have to connect it like this. And as of now, for now, we will assume the voltmeter is also ideal. Any of you, if you have studied, can you tell what an ideal voltmeter is? Or what are the characteristics of an ideal voltmeter? In terms of resistance, how much resistance should it have?
infinite resistance.
It should have infinite resistance, correct. See, when we connect an extra element like this in parallel, what happens is the current that enters at this junction now has 2 paths to split along. Originally, all the current would have gone through the resistance R1, but when you connect a voltmeter in parallel like this, some current gets deviated. Fine. But if this voltmeter has infinite resistance, no current will go that way. All the current will continue going through R1 itself. Okay. So an ideal ammeter's resistance is 0. An ideal voltmeter's resistance is infinite. Okay. And galvanometer is also a device we use to measure currents. It is usually used to detect currents, small currents. Okay. Next point. Tell me, how does resistance depend on the length of a conductor?
Directly, sir.
Okay. We know R is equal to rho L by A. Okay. If the resistivity rho and area of cross section A are uniform, then resistance is directly proportional to length. Okay. Don't simply say resistance is proportional to length. Resistivity and area of cross section should be uniform. Only then it is proportional to length. Okay. So in a uniform wire, okay, what do we mean by uniform wire? The metal should be same everywhere, or the material should be same everywhere. So the resistivity will be same everywhere. And the area of cross section also should be same everywhere. Such wires are called uniform wires. In a uniform wire, since resistivity and area are uniform, you can say that resistance is proportional to length of the wire. We'll be using this idea in meter bridge. Okay, to do calculations using a meter bridge. And tell me, how many resistors does a Wheatstone bridge have?
4, sir.
Yes, why only 4?
So the one in the middle will be neglected, right? So
But it is there, no? You
yes,
will
sir, it is
neglect
there.
it when the Wheatstone bridge is balanced. When it is unbalanced, you cannot neglect. Okay, only in the balanced condition it can be neglected. Anyway, Wheatstone bridge is an arrangement of 5 elements, no 2 in series, no 2 in parallel. But when R1 by R2, that is the ratio of resistances on the left hand side, is equal to R3 by R4, that is ratio of resistances on the right hand side, you will see that no current passes through the middle resistor R5. In that case, it can be ignored. Okay. So we use this idea also. The idea of a balanced Wheatstone bridge also is used in the working of a meter bridge. Okay, fine. Can any of you tell me what a meter bridge is used for? What do we use this device for? If you have studied.
It
Okay.
is used to measure
Continue.
measure an unknown resistance.
Right. To measure an unknown resistance. Have any of you done the experiment based on this? I won't ask any question, just to know if any of you have actually done the experiment and used it or not. Not yet. Fine. Fine. So, okay. Yeah, in lab itself, of course. Fine. Some of you have done. That's fine. So you'll be given a wire or maybe a resistance with nothing written on it. So you can't directly see and tell its resistance. You have to measure. You have to perform the experiment and find out. Okay. So this is the basic circuit diagram for a meter bridge. Understand the components. Now these gray strips that are shown here, these are all metal strips. You can see in the actual photograph on the right side. Okay. This one, and this one. These three are all the metal strips. Fine. And there are two slots available in that metal strip or between those metal strips. One is here. This is, you can call it as slot 1. In the diagram on the right side, this is slot 1. In the photo on the right side, yeah, that is slot 1. And then this one is the second slot. In the actual instrument, it is here. Okay. Now in one of these slots, we connect a known resistance. Okay, we need to have one known resistance. And in the other slot, the wire or the box whose resistance you have to calculate, you have to measure, will be connected. Okay. So in the actual photograph, if you see, in first slot, by connecting wires, you will connect a resistance box here, whose resistance is known. We can set. Okay. And in the other slot, the unknown resistance will be connected. It could be anything, as I said, it could be a wire, or they can give you another box whose resistance is not mentioned. So known, let us denote it by R. Unknown resistance, let's denote it by S. That is what you see on the circuit, in the circuit diagram also. Okay. Now, why is this called a meter bridge, first of all? You see, there is a wire connecting these metal strips. There is a wire which is exactly 1 meter long. Okay. In the photograph, it's not clearly visible. You can see a scale here, right? Meter scale. That scale is exactly 1 meter long. It's a meter scale. On that meter scale, a wire will be there. It's silver colored. Okay, usually it's an aluminum wire. Fine. In that photograph, you're not able to see it, but it will be there parallel to that scale. On that scale itself, it will be there. Okay. Since that wire is exactly 1 meter long, we call this instrument as a meter bridge. Now that wire, the wire which is 1 meter long, it has significant resistance. You can't ignore its resistance. Okay. So yeah, there is one known resistance R. There's an unknown resistance S. And this wire, the 1 meter long wire, it's called the meter bridge wire. It also has some resistance. And you see there is a galvanometer also. Okay, as we have just discussed, galvanometer is a device used to detect current. Fine. Now, where is this galvanometer connected? One end is between R and S, as you can see in the circuit diagram. Okay. From there, the wire is connected to the galvanometer, denoted by G. And the other end of the galvanometer is actually free. You can connect it wherever you want. Okay. At the other end of the galvanometer, you will find a pencil-like device. It's called the jockey. Using that, you can connect the galvanometer's other end to whichever point of the circuit you want. Okay. So in this actual photograph, if you see, there's this connector. From here, we connect a wire to the galvanometer box. In lab, you will see that galvanometer is a box-like device. Its needle can deflect both ways. It can show you the direction of current also, which way the current is flowing. And at the other end of the galvanometer, this is what I was saying. This is that pencil-like object. It's called the jockey. You connect it to the other terminal of the galvanometer, and then that other terminal can be brought into contact anywhere along this meter bridge wire. Fine. So in the circuit diagram also, that is what they are showing here. At B, one end of the galvanometer is connected. One terminal of the galvanometer is connected. The other terminal of the galvanometer, D, is free. You can make it touch anywhere along the wire AC through the jockey. Okay. And then there is a battery, EMF E. There's a key, as always. You should have a facility to switch off the current whenever you want. So this is the basic circuit diagram for a meter bridge. Okay. Now let us understand how it works, how to actually use it to measure an unknown resistance. As I said, we first connect a known resistance here, R, then an unknown resistance here, let's call it S. This is what we have to calculate. What we are now discussing is the theoretical part, how to do it. Okay. The wire AB has some resistance. Let's say its resistance is R0. Okay, the total wire AB's resistance is R0. And it's very important that the wire AB is perfectly straight and it is uniform. Uniform means it should have the same area of cross section throughout. Okay. Now, length of the wire AB is exactly 1 meter. You can write it as 100 centimeters. So for 100 centimeter length, the resistance is R0. Then for a length L, how much will be the resistance? Can any of you tell? I said it's a uniform wire, so resistance is proportional to length. So for 100 centimeters, if the resistance is R0, for L centimeters, how much will the resistance be? Simple proportionality, so you can divide. You'll get 100 by L is equal to R0 by some resistance. Let's call it R. So 100 by L is equal to R0 by R. That means resistance in a length L is equal to R0 into L divided by 100. Okay, since resistance is proportional to length, you can write it this way. In a length L of that wire AB, the resistance is R0 L by 100. Okay, you have to remember that length L is in centimeters now. Okay. Now, see, in this diagram, I have not shown you the switch. So assume switch is closed already, current is flowing. Current from the battery, okay, obviously this is a positive terminal, so current goes this way. When it enters this junction at A, some current passes through this wire, the wire of the meter bridge, and some current goes through these metal strips. So there are two paths for current. So some current goes this way and some current goes this way. Again, they'll combine and go through the battery. Okay. Now listen. This galvanometer is connected between R and S. The other end of the galvanometer, let's say it is connected at A itself. Okay. It is a detachable connector. Like you just touch the jockey at the jockey, which is connected to the galvanometer at the point A. Let's call that contact point as C. As of now, C and A are same. Okay, galvanometer is connected at one end of the wire A. Okay. Now what will happen? Do you think the galvanometer will deflect or not? I mean, will current pass through the galvanometer or not? Okay, this may be slightly difficult for you to answer. Let us think of it this way. Just a moment, I'll copy the diagram. Okay, so let's forget about the galvanometer being connected at point A. Let's say it is randomly connected somewhere here along that wire. That contact point, we are going to call it as C. Now you observe the diagram. There are obviously two resistors, R and S. Let's name them. This is the first resistance. This is the second resistance. Let it be. Now the galvanometer, as I said, you'll learn about it in the next chapter, but it has a coil wound inside it. Okay, there is a lot of wire inside it. Obviously, it offers some resistance. Okay, so the galvanometer itself has some resistance. So that's the third resistance. And AB, the wire AB has significant resistance, as I told you. Now from A to C, there will be some resistance. Let's call it as the fourth one. And from C to B, there will be some resistance. Let's consider that as the fifth resistor. So totally there are 5 resistors in this diagram. Okay, you can always split a single resistance into 2. Nobody will say no to that. So A to B was one wire. We are now considering it as 2 separate parts, AC and CB. So totally there are 5 resistors in this. Okay. Now tell me, are the 5 resistors connected like a Wheatstone bridge or not? The 5 resistors that you see in this circuit, are they in the form of a Wheatstone bridge or not?
Yes, sir.
They are. You can see 2 resistors on the left side, 1 and 4, 2 on the right side, 2 and 5, and the middle one is 3. I just numbered them like that. We'll change the numbers, not an issue. Okay. So let's call resistance R, which is a known resistance, as R1. And the resistance AC, resistance between A and C, let's take that as R2. The unknown resistance is R3. Resistance between C and B, take it as R4. And the resistance of the galvanometer, call it R5. So these are the 5 resistors in this Wheatstone bridge. Fine. Now current is passing. Current enters from this junction. And it will split. We had discussed there are 2 paths for it to flow. Now see, the 5th resistor may have current flowing through it, may not have current flowing through it. Now you all tell me, when will no current flow through R5 in a Wheatstone bridge? When will there be no current through the middle resistor in a Wheatstone bridge?
R1 by R2 equals R3 by.
When it is balanced, when R1 by R2 is equal to R3 by R4, there won't be any current in the middle resistor, right? Okay. Now R1 by R2 means the known resistance R divided by the resistance between A and C. Next, R3 by R4 means the unknown resistance S divided by the resistance between C and B. Okay. Now, this ratio and this ratio need not always be the same, but there will be one case, or but it is possible that they are same also. Okay. Now consider this situation. Let's say the galvanometer is connected. I mean, the other end of the galvanometer is connected at A. So the contact point C and the point A coincide. Now, if C and A coincide, what is the resistance between A and C? If C and A are at the same point, the length between them is tending to 0. Then how much will the resistance between A and C become?
Zero.
If C tends to A, if C goes very close to A, the resistance between A and C tends to 0. And the resistance between B and C, or C and B, we can write. See, if C is at A, then CB is same as AB, then that will become R0, or it tends to R0, the complete resistance of the wire. Okay. Now you see the ratio on the left-hand side. Left-hand side ratio will be R divided by resistance between A and C. Right-hand side, the ratio of resistors is S divided by resistance between C and B. Now this value is tending to R0. So right-hand side is a finite value. But RAC is tending to 0. If RAC tends to 0, the ratio on the left-hand side tends to infinity. There is no way these two can be equal. Okay. So when the jockey of the galvanometer is connected at A, the ratio of resistors on the left side of the Wheatstone bridge cannot be equal to the ratio of resistors on the right side of the Wheatstone bridge. Okay, because AC length tends to 0, and if AC length tends to 0, AC resistance tends to 0. So left-hand side ratio is not equal to right-hand side ratio. Therefore, the Wheatstone bridge is not balanced. Now you tell me, if the Wheatstone bridge is not balanced, will there be current through the fifth resistor or not? Fifth resistor is the galvanometer itself. Will it show any deflection or not? Current flows, it will show deflection. Okay, not a big deal also. You can directly tell. Okay, and observe the ratio once again. The left-hand side resistance ratio was infinite. Right-hand side resistance ratio was finite. Okay, and since they are not balanced, they are not equal, current will flow in the fifth resistor, means current will flow through the galvanometer and it will show deflection. It will indicate that current is flowing. Okay, now imagine doing this. You remove the jockey from the point A and connect it at some other point like this. Still quite close to A compared to B, but not exactly at A. The distance is now not tending to 0. It's non-zero now. Significant non-zero value. Okay. Now you see the left-hand side ratio. It is R divided by resistance between A and C, and right-hand side ratio is S, the unknown resistance, divided by resistance between C and B. Earlier, what was happening? This ratio was tending to infinity because RAC, I mean, the left-hand side ratio was tending to infinity because resistance between A and C was almost 0. But now this is finite. This is also finite. Okay. Earlier, the left-hand side was too large compared to the right-hand side. But now what we are doing is, we are increasing the denominator of the left-hand side. So the left-hand side value will come down. The ratio value will come down. Right-hand side ratio value will increase. Why? Because RAC is being increased while RCB is being decreased. If you move the connector to the right side, this length is not the total length of the wire, no? So the resistance from C to B will not be total resistance R naught now. It will be less than that because the length has decreased. So effectively what we are doing is, by shifting the jockey away from A, okay, and for shifting, we don't actually drag it on that wire like this. We have to lift it up from A and put it at the next point, maybe 1 centimeter after, from A, 2 centimeters from A, like that. We like pick up the jockey and connect it at the exact point where we next want it. Okay, we don't slide it along that wire. There are some reasons for it. We'll discuss experiments and all. We'll discuss later. So when the connector was at A, when the jockey was connected at A, left-hand side ratio was too large, right-hand side was finite. But now what we are doing is, we are decreasing the left-hand side ratio and we are increasing the right-hand side ratio. Okay. So as we keep moving the connector C or the jockey C away from A, this ratio will go on decreasing. From infinity, this will keep decreasing. And this ratio will keep increasing. Okay. In fact, you can imagine, if you take the connector C all the way to B, the other end, left side ratio will be finite, right side ratio will become infinite, because resistance between C and B becomes 0. If resistance between C and B becomes 0, right hand side ratio will become infinite. Okay. So when the jockey is connected at A, left side ratio is infinite. When the jockey is connected at B, right side ratio is infinite. Then definitely there will be some point in between A and B. Okay. There will be some distance from A. Let's call it L, at which if you connect the jockey, the ratio on the left hand side exactly equals the ratio on the right hand side. Do you all agree with this or not? Should there definitely be some point between A and B at which the ratio of resistances on the left hand side becomes equal to ratio of resistances on the right hand side? What do you say? It will be. Okay. Fine. So what we do experimentally is, we keep shifting the jockey away from A step by step. This means small distance by small distance. We keep shifting it away till we come to that point where the Wheatstone bridge becomes balanced. But one of you tell me, how will we know if the Wheatstone bridge has become balanced or not?
Sir, the reading on the galvanometer, it should be 0.
The only thing which indicates us anything in this diagram is the galvanometer. Fine. So as you keep shifting the jockey away from point A towards point B, at some point in between, I'm not saying exactly the midpoint, but at some point between A and B, you will see the galvanometer showing 0 current. When the galvanometer is showing 0 current, it means there is no current through the fifth resistor. Okay. So you can say that when current in the galvanometer Ig becomes 0, the Wheatstone bridge is balanced. And what does that mean? It means the ratio of resistors on the left-hand side has become equal to the ratio of resistors on the right-hand side. And what was our aim? Our aim was to calculate the unknown resistance S. So you can calculate it this way. S is equal to the known resistance R multiplied with resistance between C and B divided by resistance between A and C. And if you remember, AC, CB are part of the same wire. Okay. So the ratio of those resistances will be the ratio of the lengths. A to C, we are taking the length as L. Okay. Then C to B, the length will be 100 minus L in centimeters. 100 is in centimeters. L also should be in centimeters. So this becomes 100 minus L divided by this part is L. Therefore, the unknown resistance S becomes known resistance R multiplied with 100 minus L divided by L. And I suggest you don't remember this formula because here we are taking the length from A as L. Now, what is the guarantee that in the question that you see in your final exam, you will be given that length itself? You may be given length L as the length from the other side. Then the equation will change. Okay. So don't remember the formula. Remember the idea. It's all based on Wheatstone bridge. So in one slot, you will have the known resistance. In another slot, there will be the unknown resistance. So those are two resistors. And this meter bridge wire that is there, wherever you make the jockey touch the wire, left side of that will be taken as one resistor, right side of that will be taken as another resistor. So 4 resistors now, and the galvanometer itself is the fifth resistance. That is how you get a Wheatstone bridge here. And at some point along that wire AB, when the jockey is connected, you will see that the galvanometer shows 0 deflection. That is when you can be sure that the Wheatstone bridge has become balanced. And see, in the exam, they may put the unknown resistance on this side and the known resistance on that side. Then also the equation will change. Okay, like the ratio will change. Fine. So don't remember the final formula. Remember the circuit, remember the idea. It's very important to visualize the circuit diagram when you solve problems based on meter bridge. Okay. There's one more instrument, potentiometer also. We'll talk about it later. There also, if you remember the circuit only, you will be able to answer the questions properly. Okay. And there are some terms, just one term that you need to know, that length L. Okay. Where you see the current through the galvanometer becoming 0. That is the length where the Wheatstone bridge becomes balanced is called the balancing length. Okay. When Ig is equal to 0, the length L is called the balancing length of the meter bridge. And in the question, they will have to tell from which side the length is taken. Okay, there's no rule that you have to measure the length only from left side. And they'll mention that in the question. Okay, is the idea clear to all of you? How we are using the concept of a balanced Wheatstone bridge and also the concept that resistance is proportional to length in a uniform wire. Okay, if you have any doubts, you can ask. Okay, so let's discuss one direct question based on this, then some and some slightly different kind of questions we'll discuss. And see, for the functioning of the meter bridge, this resistor doesn't matter at all. Okay, because this is the Wheatstone bridge. And based on the balancing condition of that Wheatstone bridge itself, we can find out the unknown resistance S. So the extra resistance which is near the battery need not be considered. Now, actually what happens in a real situation, batteries offer resistance. Okay. In a real cell or real battery, there will be some resistance. It's called the internal resistance of the cell, which is the next thing that we'll discuss in this chapter. So usually beside a battery, they show a small resistance. But in this case, that resistance does not affect your measurement in any way. Okay. So well, let's take one question. Assume this resistor is resistance is 10 ohms and the balancing length from the side B is 40 centimeters. How much is the unknown resistance? Calculate and type your answer in chat, all of you. When it is like this, we see that the current in the galvanometer is 0. In questions, in exam questions, they write it this way. The galvanometer shows no deflection when the jockey is connected at so and so length. Okay, showing no deflection means there's no current passing through it.
So what is length of AB? We take it as 1 meter.
In a meter bridge, it need not be told to you. It's always 1 meter. Okay. If it's something else, they'll have to specify. If they don't specify, you have to take it as 1 meter. What happened? I got only one answer till now. One is 20 by 3, one is 15 ohms. We'll see. Current in the galvanometer has become 0, means current in the fifth resistor has become 0. So it's now a balanced Wheatstone bridge. Just write the condition of a balanced Wheatstone bridge, you'll get the answer. I got two more answers, 115 and 120 by 3. We'll see. Okay, it's a balanced Wheatstone bridge. Let's write the balancing condition. Yashmit, you tell me, what is the ratio of resistors on the left hand side? I'm not asking the exact ratio, at least the names or anything you can tell. How do you write ratio of resistors on the left hand side?
Oh, what R and for 100 minus 40.
Okay.
So
Resistance R and resistance between A and C. Okay, you are saying it is
Yeah.
100 minus 40, let it be. What about ratio on the right hand side? Or what are the resistors on the right hand side?
S and R CB.
Resistance between C and B. Okay. And we know that this Wheatstone bridge is balanced. The current in the galvanometer has become 0. So these two are equal. Therefore, the unknown resistance S becomes R multiplied with resistance between C and B divided by resistance between A and C. R is known to us, 10 ohms. And RCB divided by RAC will be equal to length from C to B divided by the length from A to C, because they are part of the same uniform wire. Okay. And what is the ratio of those lengths? C to B length is 40 centimeters. That means the A to C length will become 60 centimeters. That's all. Centimeter, the unit will get cancelled. Therefore, the unknown resistance S becomes 10 into 40 by 60 is 2 by 3. The answer is 20 by 3 ohms. Those of you who gave the answer as 15, I think you used the formula. That's why I said don't remember the formula. And others, if you have any questions, you can ask. Okay, hope this is clear to all of you. Some of you gave the answer as 15. That is not correct. So always get the picture of the circuit in your mind before you solve the problem, and the concept also. This is purely based on balanced Wheatstone bridge and resistance being proportional to length. Okay, so just write the balancing condition. You can find out the unknown resistance. There's no need to remember the formula also. Okay. Now see, I told you, like when you're actually performing the experiment, what you will do is you will connect the jockey first very close to A. Okay, you have to find out the balancing point. No, you don't know where it will get balanced. So you'll start from one end, obviously. So you'll connect it very close to A. Now there is a meter scale. As you can see, there's a scale here parallel to the wire. Okay, that scale is what tells you at what length the Wheatstone bridge is getting balanced. The scale has to be in parallel to the wire AB. Let it be. Now, suppose there is a scale on which the divisions are in centimeters. Let's say you don't see millimeters, you only see centimeters on it. Okay. So first you will connect the jockey at A itself. Fine. What is the next point where you will connect? Like at A, definitely the Wheatstone bridge won't be balanced. You will have to move the jockey away from A. You'll have to move the connector away from A. And you have to take it step by step. No, you don't know where the balancing point is, or you don't know what the balancing length is. So A is like 0 centimeter mark. Where will you next connect the jockey? Means at what distance will you next connect the jockey? I'm telling you the scale has only centimeter markings on it. It doesn't have any other markings. Any answer? You will connect it at the next possible length that the scale can indicate. After 0 centimeters, what is the next length the scale can indicate? I said only centimeter markings are there on it. What is the next length that it can indicate?
1 centimeter.
1 centimeter, you'll connect it at 1 centimeter. Okay. Fine. So first case, AC tends to 0. Next step, like when AC is equal to or tends to 0, you'll see that the galvanometer shows deflection. So it's not balanced yet. The Wheatstone bridge is not balanced yet. So you'll have to increase the length from A to C. So the next point where you can connect the jockey is the next reading where you can, the next reading that the scale can show. Okay, so the next point you will connect is 1 centimeter. Okay, then what will happen when you shift it just by 1 centimeter? Let's say it's still not balanced. Okay, observe the diagram. Assume you connect the galvanometer here now at 1 centimeter. Fine. Now AC length has increased. From 0 it became 1, and CB length from 100 it becomes 99. So on one side you are increasing the length, on the other side you are decreasing the length. And when you do that, we have already discussed, if length AC is increasing, it means the left hand side ratio is decreasing, right hand side ratio is increasing. Let it be. It's still not balanced, as I said. Okay, so the current will still be flowing through the galvanometer. It will still show you deflection. But what you will now observe is the deflection is slightly less than the previous value. Slightly lesser amount of current will be flowing through it. Okay, when the jockey is connected all the way at A, you will see more current flowing through the galvanometer. If you shift it slightly away, you will see the current decrease. You shift it further away, the current in the galvanometer decreases further. That is how you can realize that you are approaching the balancing point or the balancing length. Every time you disconnect the jockey and place it at another point and on the wire AB, you'll have to look at the galvanometer, what reading it is showing, whether it is deflecting or not. Okay. So keep shifting the connector away from A, the galvanometer current decreases. And at one point, when you connect to this wire, you'll see that the galvanometer current becomes 0. So let's say all this while, as you shifted the jockey from A to C, let's say the galvanometer was deflecting to the right side. Large deflection, then a slightly small deflection, even smaller deflection, and finally 0 deflection. Okay, the galvanometer exact device I'm not drawing. I'm just showing you the needle randomly. What do you think will happen when you connect the jockey on the right side now? Like, make it go beyond the balancing length. Connect it somewhere here. So now the distance from A to C is more than the balancing length. So galvanometer will have current flowing through it. In which direction will the needle deflect? Same direction as before, or now the other direction? It will deflect the other way because now current will be flowing in the reverse direction through that middle resistor. Okay, if you want, you can solve problems and check this, but you'll have to take the problem of an unbalanced Wheatstone bridge. That's a lengthy case. Okay, so what I'm telling you is, suppose the resistors on the left hand side are like this: 10 ohm, 20 ohm, and right side the resistors are like 5 ohm and okay, wait, right side will take a slightly bigger one. I mean, slightly higher resistance, say 15 ohm and 30 ohm. If it is like this, it's balanced. The Wheatstone bridge is balanced, then you won't see any current in the galvanometer in between. What I'm saying is, when you connect the galvanometer on the left side of the balancing point, this resistance will be less. This side resistance will be less, like maybe 15 ohms. And right side resistance will be more, make it 35 ohms. Now it is unbalanced and the current will flow in a particular direction. You can take this as a circuit and solve if you want. You can find out the direction of the current in the fifth resistor. Now you keep shifting the galvanometer, you'll reach the balancing point, cross the balancing point and go to the other side. When you cross the balancing point and go to the other side, the left side resistance will become more. AC length will be too much, no? It will increase. Right side resistance will decrease. Okay, maybe it becomes like this, 25, 25. Now again, it is unbalanced. But this time, left side ratio is less, right side ratio is more. You'll see current flows in the other direction through the fifth resistance. The direction of current through the middle resistor will change. Fine. So, as I said, you connect the galvanometer first, very close to A. I mean, the jockey of the galvanometer. It's first connected very close to A, and then we start shifting it away. Galvanometer needle approaches 0, 0, 0. Then it comes exactly to 0 at one point. That is where you get the balancing length. Let's say this is the balancing length, L. When you connect the jockey on the other side of the balancing length, you will see the galvanometer deflecting in the other direction. Current will again start flowing through that middle resistor, but in the reverse direction. Okay. Now think and answer, think carefully and answer. I told you it's a scale having 1 centimeter markings. Is it compulsory that when you shift the jockey 1 centimeter by 1 centimeter, okay, is it compulsory that at some marking, it will definitely show 0 current? The galvanometer will definitely show 0 current. Is it compulsory? Is it guaranteed that you will definitely get one point where the galvanometer shows 0 deflection? I mean, when I say get one point, I mean, when you shift it 1 centimeter by 1 centimeter, when you shift it in steps of 1 centimeter, is it guaranteed that the galvanometer will show 0 current somewhere?
No, sir.
It's not necessary. Okay, why? Any answer?
It can not show deflection when in between some marking.
See, actually the balancing length may be some 30.2 centimeters. The actual balancing length could be 30.2 centimeters, but on the scale that is given to you, you only have centimeter markings, means you have 30 centimeters, next you have 31 centimeter. So you'll place the jockey at 30 centimeter marking. You'll see that the galvanometer is showing deflection. Next, you'll shift it to 31 centimeter marking. Then you will again see that the galvanometer is showing deflection. And you go on like that, you will never get a balancing length. Does it mean we can never find out that unknown resistance? Or how will you find out, or how will you get to know that something like this is happening? How will you get to know that you have crossed the balancing length? Any idea for that?
When the galvanometer deflects in the opposite direction.
Correct. Okay. That's what I just told before. On the left side of the balancing length, you will see current flowing in one direction through the fifth resistor. The galvanometer deflects in one direction. Maybe to the right side it deflects. The needle points to the right. When you cross the balancing length and you connect the jockey somewhere here, the needle will deflect the other way. Okay. That is how you realize that you have crossed the balancing length. Fine. Okay. So that's one point you need to remember. Next, the scale that is given to you, it will definitely have its limitations, right? It will have some least count. Now, I said in the last example, I considered a scale, or I asked you to consider a scale which has 1 centimeter markings on it. That means its least count is 1 centimeter. One of you quickly tell me, what is the least count of the usual scale that we use? Usual 30 centimeter scale that we use?
It will be 1 mm, sir.
1 mm, 1 millimeter, right? Yeah. So you have steps of 1 millimeter. So see, suppose that scale is used. I am not saying 30 centimeter scale, 1 meter scale only with 1 millimeter markings. Let's say that scale. In 1 meter, how many millimeter markings will you have? 1 meter is how many millimeters?
Sir, we'll have 1000 markings.
Ha. On a 1 meter scale, there will be 1000 millimeter markings. Now your aim is to find out the balancing length. You won't keep shifting millimeter by millimeter, because that way you'll have to look at the galvanometer 1000 times. Okay, maybe less, somewhere between you will get the balancing length, but still a lot of times you'll have to shift the jockey and keep looking at the galvanometer. So you won't keep shifting millimeter by millimeter. How will you shift? Suppose you want to perform the experiment quickly, or you don't want to look at the galvanometer so many times. What is a better way to do it?
Sir, first we'll consider markings by centimeter, and once we get that point, we'll shift to millimeters.
Okay, correct. As I said, let's say the balancing length is 30.2 centimeters, means 302 millimeters is the balancing length. Now you won't go 1 mm, 2 mm, 3 mm, so on up to 302 mm. That will take a lot of time. What you can do is you can jump in steps of 1 centimeter, like connect it exactly at A, you will see that it deflects. Next, connect it at 1 centimeter marking. You have millimeter markings also, but go off directly to 1 centimeter marking. If you see that it still deflects in the same direction, it means you have not crossed the balancing length, right? So that way you can move. Let's say this is exactly this marking is exactly 30.2, that is 302 mm, 30.2 centimeters. So what you can do is connect the galvanometer at A. You will see deflection. Okay. Next, connect it at 1 centimeter away from A. Then 2 centimeters away from A, 3 centimeters, 4. In fact, you can even go in steps of 10 centimeters, not an issue. Okay. So let's say you are going in steps of 1 centimeter. Then what you will observe is when you connect the jockey at 30 centimeter marking, the galvanometer shows deflection in one direction. When you connect it at 31 centimeter marking, you will see that it is deflecting in the other direction. That means the balancing point is somewhere in between 30 centimeter and 31 centimeter. Now you can go in steps of millimeters. That's just a quicker way of performing the experiment, more efficient way of performing the experiment. Okay. And see if the scale has a least count of measurement, then there will be a least count of measurement to this instrument also. Actually, we can involve I mean, we can combine errors here, error calculation here. Error in measurement of length is this much, then what is the error in measurement of the unknown resistance? Such questions can be asked. Okay. Let's try one question like that. Let's say the known resistance is, okay, I'll have to show you the circuit. Let's say the known resistance is 10 plus or minus 0.1 ohms. And the scale is a usual meter scale with a least count of 1 mm. Scale least count is 1 mm. And assume the balancing length is found to be 20 centimeters from A. Now see, the scale has a least count and you are seeing that the balancing point is at 20 centimeters. Then what is the actual way of reporting this length? Can you say it is exactly 20.00 or 20.0? Okay, this is from error analysis, which is a part of units and measurements, the first chapter. In case the error is not specified, the least count of the instrument itself becomes the error. Okay, so the length should be considered as 20, that is in centimeters, plus or minus 1 millimeter, like 0.1 centimeters. So that is how you take the length. So remember this point. If no error is mentioned, you'll have to take the least count of the instrument itself as the error. If that is also not there, you'll have to take that measurement as it is without any error. Okay, fine. So unknown resistance is given. Balancing length is given. The question is to report the, known resistance is given, balancing length is given, report the unknown resistance. Now see, the known resistance has some error in measurement. The length also has some error in measurement. Then the unknown resistance that you calculate also will have some error in measurement, will have some uncertainty. So you'll have to report its value along with the uncertainty. So think of a way to do it. And here in this case, the length is given from A itself. So you can use the formula, not an issue. Just think about this first, all of you. We'll do the calculation later. We know S is equal to R into 100 minus L divided by L. And you are given R as 10 plus or minus 0.1 in the respective units. I'm not writing the units. And you are given the length as 20 plus or minus 0.1 in centimeter. How will you report the error in S? Or how will you report the unknown resistance S along with the error? That is the question. Think about it. I'll give you 2 minutes. Okay. Any answer? How to report the unknown resistance S along with the uncertainty in measurement? Okay, fine. It's quite possible that you all are not in touch with the propagation of errors, but I suggest you go through that chapter as early as possible, because if you study that just before the exam, like just before your JEE mains or anything, you won't be able to apply it that efficiently. You won't be that confident on the exam day. Okay. Anyway, and questions based on error analysis or error propagation can be asked from any chapter. Fine. So generally, I think we discussed this a few classes back also. Suppose two measurements are multiplied. Okay, why am I taking multiplication directly? Because here R is multiplied with 100 minus L divided by L. So there is a multiplication and a division. Of course, there's a subtraction also, but that's easy to deal with. Okay. So multiplication division is what I'm considering. Suppose X is equal to A into B. Okay. Or A power M, B power N directly. Okay. So it's like multiplication and division only. If M is positive number, let's say A cube, it's like A into A multiplication. Suppose N is a negative number, like minus 2. So it's like A power M divided by B square. So that takes care of division. So this generally represents multiplication division together. Okay. And in case of multiplication and division, if the errors are small, okay, percentage, or if not percentage, relative error also you can go for. Relative error in X, that is the absolute error in X divided by its actual value, okay, is equal to M times relative error in A plus, okay, N times relative error in B. And I told you M and N could be positive numbers or negative numbers, but in errors, you will never do subtraction. In error calculation, you will never do subtraction. So it's better to take modulus. So irrespective of whether there is multiplication or division happening, errors will always get added. Okay. Fine. And there could be a B, C to the power of P also. Then you will get plus modulus of P times absolute error in C divided by the value of C, measured value of C. Okay. Now look at what we have here. S is equal to R into 100 minus L by L. So you can write this as S is equal to R to the power of 1, 100 minus L to the power of 1 divided by L. I'll write it as L to the power of minus 1. That's all. Therefore, I can say delta S by S is equal to relative error 1 into relative error in R. So delta R by R plus 1 into error in 100 minus L divided by the true value of 100 minus L plus, although the power is minus 1, errors never get subtracted, so it will become plus 1 into delta L by L, absolute error in the length. Okay. Now delta R by R, we know R is 10 plus or minus 0.1, no? So this is the true value, this is the absolute error. So we have delta R, we have R. Next, delta L by L, we have delta L 0.1 and we have the original length. I mean the measured length is 20. Okay. The only other thing we need is 100 minus L. Now you all tell me at least this. If L is 20 plus or minus 0.1, okay, I'll write it here. How much is 100 minus L? How much is 100 minus L? It's quite simple. Don't think too much.
Sir, is it 80 plus or minus 0.1?
It will be 80 plus or minus 0.1. Now see, L is 20 plus or minus 0.1 means L ranges from 20 minus 0.1, that is 19.9, to 20 plus 0.1, that is 20.1. These are the possible values of L from 19.9 to 20.1. Now you subtract that from 100. 100 minus 19.9, becomes 80.1. And 100 minus 20.1 becomes 79.9. So this value ranges from 79.9 to 80.1. You write that as 80 plus or minus 0.1. That's all. So this is the calculated value of 100 minus L. So this becomes the true value of 100 minus L. And this becomes the error in 100 minus L. That's all. Now substitute everything here. Delta R was 0.1. Actual value of resistance was 10. Error in 100 minus L is 0.1. Actual value of 100 minus L is 80. Error in L is 0.1. Actual value of length is 20. That's all. You get delta S by S. Okay. Calculation you can do on your own. So delta S by S is known to us. Let's call it as C. Okay, that calculation, let's call it as C. Then you can tell the error in S. That is C multiplied with the true value. C we calculated. What is the true value now? For true value, you use the formula as it is. Substitute R, substitute L20. You can tell the unknown resistance S. Okay. Put that unknown resistance here. You will get the error in resistance, and therefore finally you report the unknown resistance like this. The true value that you calculated plus or minus the error that you found out. Okay. Anyway, these are slightly high level questions. In mains, they may not ask questions like this, but in advanced, it's quite possible. Okay. Especially this is an actual experiment that you will have in your 12th class. Okay. So you will have to know how to do error calculations in measurements. Okay. Fine. So that is all there is to discuss about meter bridge. So one of you quickly tell me, what is the principle behind the working of a meter bridge? Principle behind the working of a meter bridge.
Wheatstone bridge.
Balanced Wheatstone bridge, and also that in a uniform wire resistance is proportional to length. Both ideas are used here. Okay. Yeah, balanced Wheatstone bridge is the main thing. Fine. Okay, if you have any doubts, you can ask. Okay, little bit is left in this chapter. Cells, internal resistance, cells in series, parallel, that maximum power dissipation theorem, all that we will cover in the next class. And after that, there is one instrument called potentiometer. They have removed it from NCERT. So we will not discuss it now. At the end, once we finish the 12th class syllabus, if time permits, we will talk about potentiometer. Okay.
So will RC circuits be covered in this chapter?
I'm coming to that point. Yeah. So potentiometer will not discuss. The another thing that is left is RC circuits. Okay. Simple cases of RC circuit we will discuss. Okay. So yeah, next class we'll talk about cells, internal resistance, cell combinations. After that, RC circuits, and that's all there will be in this chapter. Are you all comfortable with those cube resistance questions? Like in a cube, all 12 edges are taken as resistors, and they ask you what is the effective resistance across the body diagonal, face diagonal, across one side of the cube. Are you comfortable with those resistance questions? If you are not, then we'll have to discuss that also. Okay, anyway, we'll first talk about cells, then we'll talk about RC circuit. Then, if you want me to discuss, I'll discuss those cube questions as well. Fine. So tomorrow I'll send you a worksheet based on this and also some of the previous concepts, because there's nothing much to like ask in a meter bridge. You just need to be comfortable with those error calculations. So 2-3 questions based on errors I will give you. Fine. And some previous concepts also we will revise in the worksheet. Okay. Thank you all. If you have any questions, you can ask.